A topic that's worth mentioning is the topic of fictitious forces. And these are what you feel when you're in a car and someone steps on the accelerator and you feel pushed in a certain direction. Or they slam on the brakes and you feel pulled in a different direction. They feel very real. I had a student several years ago who really hated the term fictitious force because it was almost like saying they weren't really there. And they absolutely are, as we're going to see. The term comes from the fact that they're not caused by one of the pushes or pulls that we listed in our list of things that could cause accelerations. In fact, the object that appears to have the fictitious force is not really the object that has the unbalanced force on it. An object appears to have a fictitious force when the reference frame accelerates. So I want to show you what I mean by that. I went to the grocery store, I went out in the parking lot and got a shopping cart, and I put a jar of pickled peppers on the bottom of the cart. It had nice octagonal sides so it didn't roll that much, but it would if you caused a massive acceleration. So here's the beginning of it. I have this can of hot peppers, and it's got flat sides so it won't completely roll in the shopping cart, but it will roll if there's enough acceleration on it. We're going to use this to try to investigate fictitious forces. Not surprisingly, when the cart is at rest, we don't see any sort of motion of the can of peppers relative to the cart. Not surprisingly, nothing happened. Why? Everything's at rest. The pickled peppers are at rest, the shopping cart's at rest, they have no velocity and no acceleration. Let's watch what happens when we start moving at a constant speed. Somewhat surprisingly though, even when the cart's moving, we don't see any relative motion of the peppers. So as you can see, the pickled peppers stayed in place. They did not appear to have any forces on them. There were no acceleration on the peppers, there was no acceleration on the cart. They both had their constant forward velocity, and as we've seen, being an object in motion and an object at rest is really just your reference frame, your perspective. Watch what happens when I'm at rest and I start moving. In other words, I put an acceleration on the cart. However, if we put enough acceleration on the cart, watch what happens. As you can see, the peppers went flying backwards. And we could say that there was a force on the peppers in the backwards direction, and that would be a fictitious force. It's not that the effect wasn't real, but it's that what really happened was that the peppers had no acceleration. They were following Newton's laws. They were objects at rest trying to stay at rest. And all of a sudden, the whole cart accelerated out from under them. So that's what caused them to appear to move backwards. There wasn't a force as we would usually see it. It looked like one because this wall accelerated into them. Works in the other direction too. So I'm going to show you a cart with the peppers in motion, and then I'm going to rapidly brake, and we'll see what direction they go. I'd like you to make a prediction first. It works the other way too. Watch what happens when I suddenly stop. So as you can see in this case, the peppers appeared to be pulled forward. There wasn't really a force on them. They were objects in motion, and they were trying to stay in motion, and all of a sudden the whole world accelerated out from under them. And this wall accelerated back into them. So fictitious forces, they arise when reference frames accelerate. The acceleration is actually caused by the reference frame and not the object itself. However, you could also represent it by drawing one of these forces on the object, and that's where they get their name.